Of rigid bodies. Now, back in chapter 2, I believe it was, we talked about equilibrium of a particle. Remember, a particle is just an object that can be treated as a single point, and particles can only have one type of motion, and that's translation motion. So when we talked about a particle being in equilibrium, what we wanted to see is that the sum of the forces acting on that particle was equal to 0. Because then there would be no resultant force pushing or pulling it to force it or cause it to translate one way or another. Rigid bodies, though, they can have two types of motion. They can have the translation motion, where the entire rigid body is translating one way or another, but can also have rotation motion. So it's no longer going to be sufficient to say that the rigid body is in equilibrium if and only if the sum of the forces is equal to 0. Okay, because let me show you, I can have the sum of the forces equal to 0, but my rigid body won't be in equilibrium. Let me take one force, how about we call it 5 pounds, I'll push towards me. I'll take another force, I'll call it 5 pounds, I'll go to you. The sum of those forces is 0. But watch what happens when I apply to the rigid body. It moves. Okay? So we didn't have equilibrium there, even though the sum of the forces is equal to 0. Something else has to be true in order for rigid bodies to be in equilibrium. Not only does the sum of the forces equal 0, but the sum of the moments have to equal 0. That means you won't have any translation. You also won't have any rotation. So we're going to be looking at that kind of thing for the first part of chapter 4. Actually, I think all of chapter 4 deals with this topic. It's just that the first part of it is 2 dimensions, and then the second part of the chapter is 3 dimensions. So we'll spend a day or so talking about how to do this with 2D problems. Then we'll spend a day or so talking about how to do this with 3-dimensional problems. So you might want to read through those first few sections, or at least look at them in the book sometime this weekend, 4.1 to 4.7. That deals with the 2 dimensions. And then if you want to read the rest of it, that's 3 dimensions. Because over the course of the next week or two, we'll be talking about most of what's in chapter 4. Now, the test that you took last time, I'm about halfway done with grading it, so I can't return it to you today. I'll have it for you on Tuesday. Okay. So let me start the sign-in sheet. I do have the quiz that you took last week, which I can return to you today. Okay, so like I said, for equilibrium of a rigid body, two conditions have to be true. First one is that the sum of the forces acting on the rigid body has to be equal to 0. And the second one that I mentioned is that the sum of the moments around any point has to be equal to 0. The first condition tells us that we won't have any translation with our rigid body, and the second one tells us we won't have any rotation with our rigid body. Now, if you go back to Newton's first law, it says that an object at rest will stay at rest as long as the resultant force is equal to 0. But if it's already moving with some constant velocity, it's going to keep moving with that constant velocity at the sum of the forces. So it's not that we necessarily have an object that's always motionless. It's an object that's obeying Newton's first law. But for our purposes, we'll just stick with the motionless situation. So if you just imagine an object that's at rest, if there's no forces and there's no moments, it's going to stay at rest. Okay? So of course, each of these equations is a vector equation, which could then produce for us some scalar equations. If we have 2-dimensional problems, then of course we would get the sum of the forces in the x direction equal to 0, the sum of the forces in the y direction equal to 0. And if it's a 3-dimensional problem, we'd have a third scalar equation that comes out of this, which would be the sum of the forces in the z direction equal to 0. Same thing with the moments. If we take the moments around the point P, that's going to be a vector which has an I, a j, and a k component. Well, in order for it to equal 0, that means the sum of the moments around P, x component has to be 0, y component equals to 0, and the z component equals to 0. So you see, in the most general sense here, we could be dealing with 6 equations, which would then allow us to solve for up to 6 unknowns. In a two-dimensional case, we would just have some of the forces in the x and the y direction. And if you remember, for two-dimensional case, where the object's in the xy plane, the axis of rotation, the only axis of rotation that you could have would be the z-axis. So we would be dealing with just the third scalar equation on the other side. So you could have 3 equations for 3 unknowns in 2D, but then if you have a 3D problem, it could be up to 6 equations, 6 unknowns, which might be a little bit tedious to solve by hand, but hopefully by this time you've been exposed to some techniques for solving systems of equations in efficient ways. All right, so I think what we'll do is we'll just jump right into a few examples here and see how it goes. So let's start with number 16. So problem 4.16. So if you have the book, you might want to open to that. You might want to open to that one and look at the figure. I'll try to draw it on the board so you see what we're dealing with here. Okay, so you see the figure that we have here in 416. We've got this rigid body. It's kind of like an upside down L-shaped piece. And this rigid body is being held in place by a few support structures. We have this pin, which is attached to some solid structure here that's holding the rigid body. So the rigid body would be free to rotate around that pin. But there's a spring over here at D, which is attached to a solid structure. And then we have this roller A at the bottom, which is up against this bigger wheel, which is fixed in place. So we're told that the spring is stretched in such a way that the spring force is 6 pounds. Now, if the spring is stretched from its natural length, remember, it wants to pull back to its natural length. So if it's stretched, it wants to pull back to a smaller length, which means it's pulling down on D. So that's why I could write that the spring force, FD, is 6 pounds going down. So the spring force is pulling down, which if that were the only thing acting on the rigid body, we would then have some rotation around this point C. Pull down on D, we would get this thing rotating in a clockwise kind of way. But down here at the bottom at A, we have this little wheel, which is up against this big wheel, preventing that rotation from happening. So the net result is everything is motionless. So it's in equilibrium, which means these equilibrium conditions are going to have to hold true. So given that the spring force is 6 pounds straight down, we're asked to find what is the force that the big wheel is exerting on the little wheel. And we're asked to find what is the reaction force at C. In other words, what force is this pin exerting on the rigid body to help hold it in place? These reaction forces, we're going to see these a lot as we go through chapter 4. A reaction force is it's just a force exerted by some external supporting body. Okay, that might be the best way for us to think about it. We might say that it's the forces I'll call it a supporting force from some external body. So that pin is holding the rigid body in its place. This wheel down here is holding the rigid body in its place. So we would have reaction forces, what we call reaction forces there. They're just supporting forces that's helping to hold everything in place. Okay? Supporting forces from external bodies. So probably the first thing that we ought to do whenever we have this kind of problem where we've got a rigid body being acted on by a system of forces and we need to do some analysis is to draw what we call the free body diagram, which is just a simplified sketch of the rigid body with all of the forces acting on it. So we would have on our rigid body here, we would have the spring force FD equal to 6 pounds going straight down from the point D. We would have the force, you see down here where the point B is, there's some kind of rod that's attached to the rigid body. So somebody's kind of hooked that on there and they're pulling straight to the right with 4 pounds of force. So we have this force here, I'll call it FB, equal to 4 pounds. And then we have the reaction forces. We have the force that the big wheel is exerting on the little wheel. We also have the force that this pin is exerting on the rigid body. Now, for these reaction forces, the forces from the support structures, we'll know something about what those forces look like if we take a look at the inside front cover of your book. If you just take your book and you open up the front cover, you should see a chart, and on one side the chart's going to have a whole bunch of support structures, and then it tells you what the reaction force will look like for that kind of support structure. Okay? I think this page is also somewhere in the middle of chapter 4, but if you just flip open the front cover, it's there. So what we'll look at the pin at C first. So we have a frictionless pin, which is down there, you know, in the bottom half of the table. So it says frictionless pin or hinge. Well, we've got a frictionless pin. And it says here that the reaction force could have an X and a Y component. So when I show the reaction force for the pin at C on my free body diagram, I'm going to have to put here FCX and FCY. Now it may turn out that one of those components is equal to 0. In some cases it may even turn out that both components are equal to 0. But we have to be open to the possibility that we could have an X and a Y component for the reaction force due to this pin. So anytime you see one of these pins, you should just go ahead and label yourself an X and a Y force, an X and a Y component for the reaction force. Now for the wheel, down at point A, if you look up in the first row of that table, they show you these things called rollers. Okay, those are like wheels. That's essentially what we're dealing with here. It says here that the reaction force is going to be a force whose line of action is perpendicular to the two surfaces that are in contact. So here we've got the two wheels that are in contact. So their common tangent line would be this one. The reaction force is going to have to be perpendicular to that tangent line, which would be the line that we see right here. Okay, so the force at A is going to be angled at that 60 degrees. Okay, because we're just talking about, if that's the common tangent, then we're talking about the common normal, which would be connecting the two centers of the circle. Well, you see that line makes a 60-degree angle with the horizontal. So we might label on here 60 degrees. So free body diagram is just a simplified sketch of the rigid body with all of the forces. If you want to put the dimensions on there as well, you can. So you have like 1.6 inches up here, 2 inches, 0.8 inches, and 0.8 inches. That might be helpful as well. If you want to put the point names, you can even put those, point A, B, C, and D.
How do you know which direction the FA?
Oh, the FA? I don't know. So what I do is I just assume one direction. If I get a positive result, then I guessed right. If I get a negative result, then I guessed wrong. Now, if you look at the picture, you might be able to reason your way through and get a pretty good idea of which way it's going to turn out to be. Like we said, this spring is pulling down on the point D, which is going to want to cause this thing to rotate in a clockwise kind of way. So point A wants to head this way. So A is pushing against the big wheel this way. Newton's third law says the big wheel is going to be pushing back this way on the little wheel. So I have a pretty good idea that FA is going to be in this direction. But maybe my thinking is off. I'll get a negative number, and then I know. So, same thing with FCX and FCY. I have no idea which way that force is going to be angled, so I assume positive FCX, positive FCY. If I get positive numbers, great, I guess right. If I get a negative number, I guess the opposite of what's right. Okay, so let's see here. We need to solve for three things. The three things that we need to solve for are FA, FCX, and FCY. So three unknowns. Like I said, in a two-dimensional problem, you could have three equations with three unknowns. You could have this equation, and this equation. Because if that rigid body were to rotate, the axis of rotation would be the z-axis coming right out towards you. Okay, so if we want no rotation, that means that moment around the z-axis better be 0.
Professor.
Yeah?
So if we have a test, you're going to provide this table?
No?
So we
You
got
gotta
to
know
know. Wow. Okay.
It's not that bad. Okay?
All right.
So, rollers, wheels, anything that's like a wheel, okay? Or has a rounded surface. Reaction force is just perpendicular to the tangent line for the surfaces that are in contact. Okay? Pins, we see those a lot. X and a Y component. The short cable that you see there, that's just a rope. We already know how to handle ropes. They can only pull in the direction of the rope. And then the last one, a fixed support. We might see one example of that later, but it's basically the same thing as a pin, but there's also a moment associated with it. We'll see that one later, maybe. Okay, but at least for now, if we can handle the first 4 categories, as we practice this, you'll see it's not so bad. Okay, but I would, if I were you, be prepared to know the different reaction forces. All right, so let's see. We have rigid body in equilibrium. So that means the sum of the forces in the x direction has to be equal to 0. The sum of the forces in the y direction has to be equal to 0. And the sum of the moments around the z-axis, the sum of the moments around any point will have a z component equal to 0. So let's start with the x equation and see what we can figure out from that. So we have a component of Fa that is in the x direction. So we'll have here Fa, and then it's going to be the cosine of 60 degrees if you want the horizontal component. Plus, we have 4 pounds at Fb. So for the time being, I'll just leave it in the most general case. We'll put the numbers in later. And then we have Fcx, which I assumed is to the right, so I put plus Fcx equal to 0. Well, that equation has 2 unknowns. Fa is unknown, Fcx is unknown. So right now, I really can't do anything with that equation. So I'm going to have to write another equation and see what happens. Let's take the sum of the moments, not the sum of the moments, the sum of the forces in the y direction. So in the y direction, I have a component for Fa that is vertical. Okay, so your components here, you go up for the y and you go to the right for x. So that's why we had positive Fa here. And we'll have positive Fa, but now sine of 60, plus Fcy minus Fd equal to 0. Well, now I have 2 equations, but I introduced a third unknown. So right now, 2 equations, 3 unknowns, still can't solve the system. We need to write one more equation. So we can take the sum of the moments around any point. I'm going to choose the point C. And the reason I'm going to choose the point C is because 2 of my unknowns, Fcx and Fcy, have lines of action that go through the point C. So I know that these 2 unknowns are not going to show up in the equation. That means the only unknown that could possibly show up in the equation is Fa. So that should give me an equation that I can solve for Fa, which I can then plug back into the first 2 equations to solve for Fcx and Fcy. So let's see if we can write this equation. Now, if we take the sum of the moments around C, because it's a 2-dimensional problem, all of these moments are in the z direction. So we're working with that third equation under the sum of the moments over there. The one that I checked off is the one that applies to 2-dimension problems. And in 2 dimensions, we can just use our F times D shortcut for all of these. All right, so let's see. Now remember the components for Fa over here. You've got a y component and an x component. Now the y component has a line of action that goes through C, so we don't have to worry about that one. But the x component, we're going to create some rotation around C. Hold the point C fixed and push to the right. That spins you in a counterclockwise kind of way. So we'll have a positive Fa cosine of 60. And the distance between A and C is 1.6 inches. The force at B, again, hold the point C fixed and push to the right. That's still going to spin you counterclockwise, so it's going to be a plus. Here we have FB times 0.8 inches. And then, like we said, Fcx, Fcy, their lines of action go through the point C, so there's no moments around the point C associated with those. D, if you hold the point C fixed and you pull down on D, that's going to spin you clockwise. So this one's going to be a minus, and you're going to have Fd times, you see the distance between C and the line of action for D is 1.6. And that's equal to 0. So if you plug the numbers in for FB
We don't need a sign.
and FD, we don't need what?
We don't need sine 60.
FA sine of 60?
But it's going to be 0, a times 0. Okay.
Yeah, because that line of action goes right up through the point C.
Okay.
So you could put it there, you could put FA sine of 60 times 0,
yeah, it's gonna be-
but there's no need because that's going to drop out of the equation anyways. So if you plug the number in for FB and FD, so put 4 in here, put 6 in here, you can solve this equation for FA. If you solve for FA, you should get 8 pounds. So it told us to find the reaction force or the force exerted on the roller at A. Well, we found the magnitude of the force, so that's not good enough to express as the final answer. I assumed the direction up and to the right. I got a positive answer, so that means the direction that I assumed is true. So when I write the force vector, I can say 8 pounds angled 60 degrees up and to the right. Now that we know FA is equal to 8, so this 8 right here, we can drop that in right here and right here. And then plug in the FB and FD that were given, and we can solve for FCX and FCY. So FCX, that one turns out to be negative 8 pounds. So that means the x component is really acting to the left. I guess to the right. I got a negative number. That just tells me in reality the x component is to the left. So I didn't really have to worry too much about my guess because now I know which way it really is. FCY, when we solve that one, we should get negative 0.93. So again, I guessed up for FCY, but in reality I got down. So the net result here is I assumed that FC was in the first quadrant. But my 2 minus signs tell me that it's actually into the third quadrant. Okay, fine, I know that now. But to express this as a vector, since there was no coordinate system given to us with this particular problem, we kind of were just assuming that we were using the standard, but that wasn't given to us. We should express this force Fc in terms of its magnitude and direction. So we're going to take here that the magnitude Fc equal to the square root of negative 8 squared plus negative 0.93 squared. We'll take the angle to be the inverse tangent of the y component divided by the x component. So 0.93 divided by not 0.8, but 8 itself. Let's see what we get if we run those calculations. So we're taking the square root of, it's going to be 64 plus whatever 0.93 squared is. So 8.05, okay. And the angle, when we do the inverse tangent, we take the 0.93 and divide it by 8, because the 2 minus signs cancel. What do we get, 6.6 degrees? So to put this into the vector form, we would say that FC, the vector, equal to 8.05 pounds. And because the x and the y components were negative, we said that FC is actually angled into the third quadrant, so I show my angle going into the third quadrant, and that 6.6 degrees means from the horizontal reference we go in a counterclockwise rotation by 6.6 degrees. So that puts you down in the third quadrant there. So that's what we call the reaction force at C. So when that spring is pulling down on the point D, like we have with 6 pounds, that pin has to exert a force that we just found down and to the right to help hold